Another part that you have to deal with is work. And again, work is basically hard for chemicals to do. Obviously, like as human beings, it's a lot easier for us to do work. So realistically, the only time that chemicals can do work is whenever we make a gas. So when we expand or when we lose gases or the gases are compressed. So we either have when gases expand or when gases contract. And if you think about it, it's kind of like when you have a piston. So down here, there's pressure on the system and the gas is being pushed or contracted. When the pressure decreases and the volume of the system gets bigger, then there's expansion. So basically, if the gas expands, then the system is doing work. The particles are literally pushing on the piston, and the energy is going from the gas particles into the piston. So it's going from the system into the piston over here. If you do it the other way, if work is done by the piston, then there's going to be compression. And again, you can use this work. This is a lot of how cars work with it. And basically, what you have to think about is if there's expansion, then the system is doing work, and if there's compression, then the surroundings is doing work, and it's going to be positive. If it's expansion, then the work is going to be negative. And we'll look at a couple examples of those to kind of help you through it. One thing you want to realize is when the gas expands, it's pushing on the piston, and the energy is going to the piston. And what you want to think about is what we said before is it's always equal but opposite. So if the gas gives so much energy to the piston, then the piston is going to gain that much energy, and that means that the system lost that much energy. And what you want to realize is it's always equal but opposite. One gains, one loses. And the first law of thermodynamics basically just says that energy is conserved. So if there's any energy that's lost by a system must be gained by the surroundings or vice versa. So this goes back to regular Chem 1, just saying that if one thing is going to gain, one thing has to lose. And then what you want to realize is there is this thing called internal energy that basically says if you sum up all your energy, either potential, kinetic, whatever, basically what you can look at is you can look at how much energy goes in and how much energy comes out. And you can look at changes over time. We're not going to take a person and rip them apart atom by atom. So what we look at is we don't look at the total internal energy. We look at the change in internal energy. So it's just kind of like how do you track energy changes in chemical systems. And just for your pleasure, you gotta love the little cat in a bow tie and cute little glasses. Okay, so we have two more slides in this section. The first one has a little diagram on it. And what you want to realize is your change in internal energy is basically how much energy your products has minus how much energy your reactants have. And basically you have two things happening. You have work being done or being done on it, and you have heat. So if your change in internal energy is greater than 0, then the system won and it gained energy. If your change in internal energy is less than 0, then the system lost and the surroundings gained energy. What you do to do your internal energy is you look at what's happening with your heat and what's happening with your work. And the way I think about it is I think of my system as one thing, and I think, okay, what's happening? So first, if I look on the right side, here is my heat. And if the heat is leaving, then my Q is negative, and we call that exothermic. So heat is leaving the system. If heat energy is being added to the system, then the Q is positive, and we call that endothermic. So I think of exothermic because exothermic's leaving. It's on the outside. I think of endothermic because it's into, so it should go into the system. Remember, the only way that you can do work is by expansion or compression of gases. So if the system expands, then work is negative. If the system compresses, then work is positive. And it's basically kind of like a bank account. You're just kind of saying, are you depositing? Are you withdrawing? And you just have to think about, am I adding the heat or am I taking away the heat? Am I adding the work or am I taking away the work? So what we're going to do is we're going to try a couple problems, hopefully so that you can kind of get comfortable with the different types. So here are 3 problems. The first ones are just work. And what you have to realize with work is all about gases. And what you have to think about is if you make gases, well, we should say make more gases, then that's expansion. And work is negative. If you make less gases than you start with, that's compression. And then work is positive. So if I look on here, and I look on the left side, I have zinc, which is a solid, and I have hydrochloric acid, which is aqueous. So on the left side, there is 0 gases. And then on the right, I have zinc chloride, which is aqueous, and I have 1 gas. So I have 1 gas on the right. So I'm making more gas. So what that means is that my work would be, if I'm making a gas, then I'm going to be expanding, and my work would be negative. But you have to pay attention to what are your states of matter, because this side there's no gas, and then on this side there is a gas. So if we do this one here for letter B, we have hydrogen gas and we have chlorine gas. So we have 2 gases on the left. And on the right, we also have 2 gases. Now you have to be careful with this because we have 2 HCl's, which are gases. They still count as gases, 2 of them. So in this case, work would be 0 because there's no work. We're not expanding, we're not compressing, so it wouldn't change. And then if we look at this last one here, on the left we have no gases, so 0 gases. On the right we have 2 nitrogen gas, 4 water gas, and an oxygen gas. So we have 7 gases on the right. So what that means that there would be expansion and work would be negative. So you have to think about, am I making gases or am I losing gases? And then these last ones down here are just thinking about kind of like what's going in, what's going out. So they're going to tell you something about work, and they're going to tell you something about heat. So if you look here, it says the gas is compressed by 462 joules. Compression is positive. So my work is positive 462 joules. And you know that just because it's compression, someone's squeezing it, so that means that the energy is going into the system. And then they say there is a heat transfer of 128 joules from the gas to the surroundings. It's leaving the system, the gas, so then our heat would be negative 128 joules. And then what you need to do to get it overall, like what's the overall energy change? So the change in energy, well, that equals your heat plus your work. So my heat is negative 128 joules plus my 462 joules, and it should end up with a positive change of 334 joules. So the overall, the system gained energy. It gained all of its energy from work, and then it lost a little bit for heat. So take a second, try the last one, make sure you're okay with it, and then I'll put the answer up there in a second. So this last one, they tell you that the gas expands. If the gas expands, that means it's doing work, which means it's negative. So it does 200 joules of work. What that means is that it's negative 200 joules. It's losing that much energy. And then if you look at the heat, it gained, ooh, I don't know what I just did. I zoomed in, sorry. But it says it gains 350 joules of heat, which means that that's positive 350 joules. And then what we want to do is we just want to add them together. So my heat is 350 joules plus my work, which is negative 200 joules. And I end up with that it gained overall 150 joules. And it's really important that you understand like this transfer of going from one to the other.